Hey everyone, and welcome. Today we're tackling a fun LeetCode problem called water bottles. It sounds simple on the surface, but it's a great example of how we can solve a problem with both a step-by-step simulation and a more optimized approach. Let's dive in and break it down. Alright, here's the setup. We start with a certain number of full water bottles. The problem gives us two numbers: the number of bottles we start with, and a value called numExchange. This second number tells us how many empty bottles we need to trade in to get one new, full water bottle. Every time we drink a full bottle, it becomes an empty one. Our goal is to figure out the absolute maximum number of bottles we can possibly drink. So the main cycle is pretty straightforward. We drink, which gives us empty bottles. Then we see if we have enough empties to exchange for new full ones. If we do, we make the trade, and then we can drink those new bottles, which gives us more empties. We just keep repeating this process until we're left with a pile of empty bottles that's too small to make another exchange. Let's walk through the example from the problem description. We start with 9 full bottles, and we need 3 empties for an exchange. The first thing we do, naturally, is drink all 9 of those bottles. So right away, our total drink count is 9, and we now have 9 empty bottles sitting in front of us. Okay, with our 9 empty bottles, can we make a trade? Yes. Since we need 3 for an exchange, 9 empties get us exactly 3 new full bottles. We immediately drink those 3. This adds 3 to our running total, so we've now drunk 12 bottles, and after drinking them, we're left with 3 new empty bottles. Now we have 3 empty bottles. Is that enough for another exchange? You bet. 3 empties get us 1 more shiny new full bottle. We drink it, of course. Our total count goes up by 1, hitting 13. After we're done, we have just 1 empty bottle left. With only 1 empty bottle, we look at the rule. We need 3 to make a trade. We don't have enough, so the cycle is over. We can't get any more water. So our final answer is the total number we drank, which is 13. Just a quick heads up. We'll be walking through the solution using Python. But don't worry if that's not your main language. The logic is the same everywhere. I'll be showing the full code for Java, C++, and JavaScript towards the end of the video. Okay, for our first approach, we'll do exactly what we did by hand. This is a classic simulation. We'll set up a couple of variables, one to track the total bottles we've drunk, and another to track our current pile of empty bottles. Then, we'll use a loop that keeps running as long as our pile of empties is large enough to make a trade. Inside that loop, we'll figure out how many new bottles we get, update our total, and then calculate our new number of empty bottles for the next round. Here's the Python code for that simulation. Let's break down how it works. We start off by initializing our variables. The consumed bottles count begins with the number of bottles we were given, because we're going to drink all of those for sure. This also means our starting number of empty bottles is that same initial amount. Next we have our while loop. This is the heart of the simulation. The condition is simple. As long as our pile of empty bottles is big enough to make a trade, we'll keep running the code inside the loop. Inside the loop, our first step is to figure out how many new bottles we can get. We do this with integer division, dividing our empty bottles by the exchange rate. We immediately add that number of new bottles to our running total of consumed bottles. The last, crucial step is updating our stock of empty bottles for the next iteration. First, we calculate any leftovers using the modulo operator. Then, our new total of empty bottles is the sum of the new bottles we just got, plus those leftovers. The loop then repeats with this new value. Okay, that simulation works perfectly. But there's a slightly different way to frame the problem that can lead to more concise code. Instead of thinking just about empty bottles, let's think about the total number of bottles we have available at any given time, whether they're full or empty. We start with a certain number. We drink some, which become empty. Then we can think of our new pool of available bottles as the ones we get from the exchange, plus the ones that were left over. Here's the code for this optimized way of thinking. It looks a bit different, but it gets to the same answer. Notice how we're only really tracking one main variable, num bottles, inside the loop. Let's see how it works. Inside this loop, the variable num bottles represents our total supply of bottles we can do something with. First, we calculate k, which is the number of full exchanges we can make right now. To make those k exchanges, we had to use up k times numExchange empty bottles. So we add that amount to our consumed bottles total. Then, our new supply of bottles is the k times new ones we just got from the exchange, plus whatever was left over. When the loop finally ends, num bottles will hold a value that's less than numExchange. Dustaprot. These are the last few bottles we had that we couldn't trade in. But remember, we still drank them. So for our final answer, we return the total we accumulated in the loop, plus these final leftover bottles. So how efficient are these solutions? Well, for time complexity, it's really fast. In each step of the loop, the number of bottles we're dealing with gets divided by about the exchange rate. This is a logarithmic relationship, which means it can handle huge inputs very quickly. For space, it's as good as it gets. We only use a handful of variables to keep track of our counts, so it's big O of 1, or constant space. Alright, as promised, here is the full solution in Java, using the first simulation approach. You can pause the video here to take a closer look at the implementation. Next up, here is the C++ version of the solution. Again, feel free to pause and review the code. And finally, here is the solution in JavaScript. Hopefully seeing it in a few different languages helps solidify the concepts. So let's wrap it up. The biggest takeaway here is that simulation is often a great starting point. If a problem describes a process, just try to code that process directly. We also saw that sometimes you can look at the same problem from a different angle to get a slightly cleaner or more optimized piece of code. And finally, this problem is a great reminder of how useful integer division and the modulo operator are for any kind of problem involving groups and remainders. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more LeetCode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the Playlist tab and find a playlist that fits your goals. Also, if you're looking for even more LeetCode problems beyond the daily challenge, I've started a second channel called LeetCode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this LeetCode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. This channel doesn't make any money from sponsorships or ads yet, so if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.